that if you won't pay attention if I hand it out first, you won't pay attention to the rest of the day. And if I hand it out second, you might pay attention. Okay, did we get everybody got a handout? There we go. Happy return from fall break. And now how many weeks? Is it 4 weeks till we get another break? Now you're all counting. Yeah.
That's where I replenish all my calories.
Oh, the yes. I'm trying to block it off. I know, but then it's sort of you can do it again if you. And I haven't decided yet whether my granddaughter can sit through the meeting or not. I have been. Yes, I can say
Maybe, I don't know.
yeah. Oh, she can sit through any.
Pretty good. Why there was never any
There you go. Oh, not sure. I just know you took that.
Yeah, so I think we only did like
Okay, so I have a fun we should get going. So the one I gave you a handout is back there. So I will at 12:15 hand back your stuff and your cheat sheets. And I left your cheat sheets in my office and graded these at home. And I sometimes wish I had these just to ask, how did you answer this question in a particular way? But I did. So that's going to be your task to find out, why did I answer this question this particular way? So, okay, but I just wanted to get a start on the new unit, and then we'll look at the test. So the papers aren't graded yet. Yeah, but I got the biochem lab papers graded. Yeah, they're ready to go. Okay, so I'm going to skip that introduction. So if you look at the syllabus last Wednesday, I was supposed to talk about an introduction to this particular unit, and we didn't. We did kind of finished up receptor-mediated endocytosis, and then we did a review. So I'm going to tell you how you can get the overview for this unit, because that's sort of going to launch in today with everyone. Okay, so for the introduction. Or the handout. Okay, so the handout is sort of an overview of chemical signaling. Okay, and we're not going to cover all of the different kinds of chemical signals. We're just going to cover, obviously, some. We just can't cover them all. Okay, so that'll help. There is a Camtasia. Okay, that is on this unit. I opened up this unit so you can see it. I think it would be probably helpful if I shut down the other two units, because I think, does that push your third unit up closer to the top? Okay, it doesn't do it for me, but if it does that for you, I'll shut down the first two units. Okay, so there's a Camtasia, and if you read pages 813 to 820 in your book, it's sort of a, these are somewhat repetitious, the handout, the Camtasia, and the book. So you should get it. Okay, there is only one figure, and then figures 15.1 through 15.8, and I will take, we're gonna fix 15.7, which kind of drives me nuts. Okay, so in this unit, which is, again, my favorite unit, it's really cool. I could just spend years on this particular unit. We are learning how to be a multicellular organism. So even yeast and other unicellular organisms do communicate with one another, but in order to be a functional multicellular organism, the cells of that organism have to communicate with one another, so they're not performing competing tasks. So they coordinate their activities. So this unit's really all about chemical signal. Okay, and we are going to cover, of all the different kinds of chemical signaling, we're going to cover the secreted signals. Okay, better say this is what we're covering. Okay, what you'll find out in the introduction is that not all chemical signals are secreted. We're going to also only look at the water-soluble signals, okay? And not cover the fat-soluble. The fat-soluble receptors, signaling and receptors are more suited for molecular genetics than they are for this course. Okay, what else can we say? But these will be both endocrine and paracrine. Well, and autocrine. Okay, and these three terms, endocrine, paracrine, autocrine, really just imply what is the source of the chemical signal. How far did the chemical signal have to travel in order to get to that particular cell? And from a molecular standpoint, who cares? Because once we get interested in it is when the signal attaches to a receptor. We don't care how far it had to travel to get to the receptor, okay? Just as long as the signal attaches to a receptor. So we're hitting all three kinds of signaling. Okay? So one of the key features of all water-soluble signals is that there is a cell surface receptor. The signal doesn't get into the cell. I'm going to say it doesn't do its job inside the cell. I was going to say it could get into the cell by receptor-mediated endocytosis, but that's not how it does its job. It's going to be, if it gets in by receptor-mediated endocytosis, it's going to be degraded, so it won't get a chance to do its job. Okay. So in order to transmit that signal from the outside of the cell, where the hormone or whatever the signal is, binds to the receptor, in order to get that signal into the interior of the cell, all of these signalings involve second messengers. So, a lot of what we're going to be covering in all of the different pathways is how do you get to the second messenger? How does it get made or how does it get released? Okay, calcium, for example, is a second messenger, and you don't make calcium, but you certainly release it from the endoplasmic reticulum. Okay, so that's going to. So we will be spending most of our time looking at what are the cell surface receptors and what are the second messengers. Okay. The other thing that's going to be difficult, I think, is that we used to think of these little pathways that are initiated by each receptor as kind of linear. Okay, they're extremely branched. So all of the pathways in the cell that you could learn them in a linear way, but the reality is they're like a spider web in the cell. And the receptor pathways cross, they compete with one another, they enhance one another. So I think the key is you gotta stay sort of flexible in your head, because we're going to see receptors and their pathways do a bunch of crazy things. Okay, so I'm gonna start out first by looking at what are the different receptors that we'll be covering. And then we'll take a look at the second vectors, and they are on your handout. So if you look on the second page of the handout or the back of your handout, they're all there. So we're going to start out with G protein coupled receptors. G protein, and they're abbreviated GPCR. This is by far the most common kind of hormone receptor. And I'm going to give you give you an assignment for tomorrow. Okay, more than half of the drugs that you can get at the pharmacy are drugs that bind to G protein coupled receptors. Okay, so what I'm going to ask you guys to do, I'll give you an example of a drug I take, but I'm going to have you guys come up with or find a drug that binds to a G protein coupled receptor, that does its job by binding to a G protein coupled receptor. Okay? It's amazing how many drugs have that capacity, function that way. So over 50%. I'm trying to think of either over-the-counter drugs. Yeah, there are even over-the-counter drugs that have this. Oh, I will give you, I'm going to give you different examples. Okay, for example, any of you use albuterol? Oh, you said, yeah. Like recently, or?
Yeah.
Did you like it?
Yeah.
Okay.
Makes you a little shaky.
Huh?
Makes you a little shaky.
I know.
Hold it.
I know. I hate that drug. So albuterol is a drug that binds to a G protein coupled receptor. It happens to be an epinephrine receptor. It is an epinephrine. This particular drug happens to be an agonist, so it mimics the effects of adrenaline. So it's like you get a adrenaline boost, as if you needed one. So it's used to open up airways. Is that right, you guys?
For what?
Open up airways?
Yeah.
Yep. Me too. Okay. So that's one drug. I would avoid it if I was going to die, actually. Okay, so what I want you to do is find some other drugs that bind to G protein coupled receptors. And so what I want to know is, what is the drug? What receptor does it bind to? Okay? What receptor does it bind to, and what is the purpose of that drug? Okay, do you need another example? PTP one. I don't know if I can get it. Yeah, and then I didn't write the name of the drug down. I think Tagamet. Why do people take Tagamet? I think you could probably find it under different names, and wouldn't you know, I didn't. Oh, Zantac, here's another one. Why do people take either one of those drugs?
Is Zantac like, is that
Heartburn.
purple?
Yeah. It's for
I think
heartburn.
that's Prilosec is purple, but maybe Zantac is purple too. Yeah. So this happens, these are both they both bind the histamine receptor. And the histamine receptor, the H2 histamine receptor, controls the proton pump in your stomach. Okay, so these are going to inactivate. Okay, so Zantac inactivates the histamine receptor, and that is going to decrease proton secretion. So it's used to treat acid, too much acid reflux. Omeprazole is actually a direct inhibitor of the proton pump by disulfide bonding to the proton pump. Okay, so I want you to find one other and answer the three questions. What is a drug? What receptor does it bind to, and what effect are you supposed to get out of that particular drug? Okay, and then email it to me so I can compile it. So in other words, you kind of have to do this before about 11 o'clock tomorrow. Okay, so we'll see what we get. I did this, I had a class do this one other year, and I spent so much time kind of fixing the handout that it wasn't worth it. But I'm gonna have a lot of faith in you guys to do that. Okay, so we're gonna spend a lot of time looking at G-protein coupled receptors. Okay, another class of receptors are just the different kinds of channels. I think we've already encountered some of the channels. In neuromuscular junction, okay? In neuromuscular junctions, the acetylcholine receptor is a sodium channel. In other parts of the peripheral nervous system, the acetylcholine receptor is a G-protein coupled receptor. Okay, so in your heart, for example, acetylcholine and epinephrine both control the rate of your heart. Both of them bind to a G-protein coupled receptor, but obviously different G-protein coupled receptors because the outcome is quite different. Epinephrine speeds up your heart, acetylcholine slows down. Okay, so that one, let's see. I think I had GABA receptor. We already covered that one. In the central nervous system, and that's a chloride channel. Okay, we're not going to cover these. There's just not enough time. And then a third class of receptors, probably the more interesting class, are receptors with enzymatic activity. are several, but there's one class that's absolutely the most common, so we're going to be covering that. And we sort of already covered these. And one is, okay, for example, the insulin receptor. And we've called these receptor tyrosine kinase. Or RTKs. Okay, and that's because when the kinases phosphorylate proteins, they phosphorylate the proteins on tyrosine residues. And that's sometimes a hint that the protein kinase is involved in cell growth regulation. Okay, so that's one kind. So we'll take a look at receptor tyrosine kinases and all of the different things this can activate. Okay, another kind that's very related is a receptor that doesn't have any enzymatic activity on this, in the cytoplasmic domain, but it recruits. A kinase, okay? So it has the same functional domains as the receptor tyrosine kinase, except that the domains are on two proteins. Okay, so there's a receptor binding site, okay? And the receptor recruits tyrosine kinases, okay? And the tyrosine kinases, the one pathway we'll look at is the tyrosine kinase is called JAK. Okay, great name, okay? And the most well-known substrates for the tyrosine kinase, JAK, is a transcription factor called STAT. So this is the JAK-STAT pathway, and then good example of a hormone that activates a JAK-STAT pathway would be erythropoietin, and what does that do? Yeah, it stimulates the production of red blood cells. It could be, erythropoietin could be also a signal or a hormone that would activate the myeloid cells that we're using in the biochem, but for some reason they don't need stimulation, and that worries me. Okay, so we'll look at the JAK-STAT pathway, probably not so much with erythropoietin, but different other kinds of signals. But we'll look at insulin and other growth factors and take a look at what gets activated from these. Okay, so you got the three. Okay, so our focus will be G-protein coupled receptors and the receptor tyrosine kinases, this kind and that kind. And I noticed, okay, so do you have on your handout receptors associated with other enzymatic activities and receptors? The one says receptors with protease activity, for example, the thrombin receptor.
The what?
The thrombin receptor. Do you have thrombin receptor on there?
No.
Oh, I fixed it. Good. Because I was just all wrong. So all of the receptors that we just mentioned can activate centrotensin. receptor tyrosine kinase, it doesn't get into the cell to do its job, but one of the things it has to do is get the glucose, that glucose that's stored in a vesicle, get it up to the cell surface. Okay, so it can't scream into the cell, hey, move your butt. So it's going to have to transmit the signal into the cell by some other mechanism, and that other mechanism is it activates a protein, a second messenger. Growth factors also bind to receptor tyrosine kinases, mostly to stimulate cell division. Okay, so that signal has to get from the cell surface, where the growth factor binds to its receptor tyrosine kinase, all the way to the nucleus. Okay, and that, of course, is going to happen by not just screaming, hey, nucleus start your division process, but there's going to be you have to synthesize a second messenger, which also transmits the message into the cell, or through the cell. Okay, so I think your handout mentions them. I'll tell you which ones we're going to cover. Which ones we cover now? Okay, so we'll first look at cyclic AMP, or sometimes cyclic GMP is used, but we're not going to see any examples of cyclic GMP. And anybody know what it's, well, so that means high, adenylyl, okay, we'll certainly look at that one. We will certainly look at calcium. And you can't make it, but it's going to have to be released from the endoplasmic reticulum. So we'll look at, so that sounds like, oh shoot, we got to think about a channel. So we will have an issue, we'll have a channel that we have to control. Okay. Okay, and phosphatidylinositol 3-phosphate. 3 meaning there has to be a phosphate group on carbon 3 of inositol. There could be other carbons, but it's got to be one. There's got to be one on carbon 3. Inositol triphosphate. And we'll call this IP. This is going to be PIP3, okay, to distinguish between the two. Okay, they look alike in terms of names, but they're quite different. And then diacylglycerol. One I wish we had time to cover is nitric oxide. That's not okay, so why do you get lactic gas at this? And we could probably come up with other second messengers, and like I said, we won't have time for nitric oxide. But you'll get the clue. I mean, you'll figure it out. What, by looking at what all of the other ones do, I don't think it would be that hard to figure out what is nitric oxide doing. Okay. Oh, I'm watching the time. Okay, I'm just going to go through one more thing and then we'll hand back the test, because there's one thing I want to spend a little bit more time on than usual. Okay. So in figure 17, or 15.7 and 15.8. Okay, these guys are looking at common proteins in the signaling pathways that we'll see. And you've already encountered these. But I don't think it hurts to go through this again, okay? And there's a huge error in I think 15.17. Oh, this is a protein. I'll put down protein kinase. So we're going to see a lot of the proteins in the signaling pathways are protein kinases. We've already seen that when we looked at IRE activates ASK1, which activates JNKK, which activates JNK. We've already seen a whole bunch of protein kinases. Always the source of the phosphate is, ATP. That is the definition of a kinase. Okay, kinases phosphorylate substrates using ATP. Okay, now here's what the book says. Oh, well, I'll finish up what the book says in a second. Let's finish up the research. Okay, the reverse reaction is done by a phosphoprotein phosphatase, and I don't think there are that many different kinds of phosphoprotein phosphatases in the cell because they just take phosphates out. Okay, so the state of the protein, whether it's phosphorylated or not, depends on the ratio of protein kinase activity to phosphoprotein phosphatase activity. Okay, so I'm going to abbreviate this PPP and this PK. So if the protein kinase activity is greater than the phosphoprotein phosphatase activity, the protein is going to be largely phosphorylated.